Hi, in this video I'd like to cover the force on current carrying wires in magnetic fields. So, in case you hadn't heard, a force is exerted on a current carrying wire that's in a magnetic field. This is because a current is really a collection of moving charges, and in a previous lecture we talked about the Lorentz force law, which among other things tells you about the force on moving charged particles in magnetic fields. Now, the direction of this force is given by the right-hand rule. Let me tell you what I mean. So first of all, we already know that there's no force on stationary charges in magnetic fields. And in a wire where there's no current flowing, there's no net motion of the charges. In other words, the free electrons might be zipping back and forth in your current carrying wire, but there's no net motion. They move up as often as they move down, for example, in this wire, which is vertically oriented. Okay, so even though there's charged particles there, the magnetic field does no net force on them because they're not moving in net. However, when you do have a current, let's say for example in this problem you have a current moving upwards through this wire, and the magnetic field is into the screen, as can be told from the green X's which symbolize an into the screen magnetic field. Remember, the X's are supposed to look like the back sides of an arrow which have the feathers on them. Okay. Now remember that current is defined as the direction of positive charge flow. So previously we learned that for charged particles moving in magnetic fields, the force is QV cross B, where F is the force, QV is the charge times the velocity of your charged particle, and B is your magnetic field. This is governed by the right-hand rule, and current is supposed to be positive charge flow. So if the current is moving upward, then that would mean that positive charges are moving upward. Using our right-hand rule, right, we have QV is our index finger, and B would be our magnetic field into the screen, and that would make the force on a moving positively charged particle to the left here, which is what we see for the current carrying wire in this figure. So that squares with what we already knew from the Lorentz force law. Now if we reverse the direction of the current, then the positively charged particles would be moving downward, and then that would cause a force to the right on our current carrying wire. Okay? I can further relate this to F is equal to QV cross B and derive a new formula for currents so that I don't have to worry about the charges individually, and I can just focus in on what the current value is. So remember that in a previous lecture we talked about a model for current, specifically the Drude model for current, which said that you had these charge carriers moving through this wire, for example, with some drift velocity. Okay? So if we define the current as the positive charge, then we can just for a second assume that our charge carriers are positively charged here, as indicated in this figure, and they're moving in the direction of the drift velocity, okay, which is the direction of the current. If they're moving that way, and then the magnetic field is into the screen, as indicated by the green X's, then your force, QV cross B, would be upwards on this wire, okay? Now, remember that you have a bunch of charges. If you have a current, you have not just one, but you have many, many moles, for example, of charge moving through this wire. So you would multiply for your total force, the force from one charge moving in the wire times the total number of charges that you have moving from that current. We'll call that big N, say, for the total. But remember, in our Drude model of current, what we said was that the total number of charge carriers that we have, big N, would equal to our charge carrier density, or the number of charges per unit volume, which we called little n, and then times the volume of the wire. Well, the volume of the wire would be the cross-sectional area of the wire times its length. And so we could say that the total force would be QV cross B times little n AL, which gives you the total number of charges in that wire. If you need a refresher on this, go back and watch that other model or other video on the current model, or the Drude model of current that we discussed previously. Now, looking at this equation again, here we have QV cross B times little n AL, remembering that our current we defined as little n Q times the drift velocity times A, our cross-sectional area. Okay, so that was our definition for current. And so subbing that in, then what we can see is that we have F is equal to IL cross B. Okay? So what happens is the the little n, the q, the v sub d, and the a, that gets sucked up into our current. That's our definition of our current, leaving L, which is the length of the wire there, times the current, okay? And that's where the F is equal to IL cross B comes in. So now we don't have to worry about what's going on with the charge carrier densities or anything like that in our wire. We can just measure what the current is, and we can measure the length of the wire and then determine the force that a current carrying wire would experience in some magnetic field B. Okay? Yet again, this is a cross product, a vector cross product, so it's governed by our right-hand rule. Remember the two, the gun, right, and stop in the name of love. Okay? So in this one, IL would be your index finger, B would be your middle finger, and your resultant force would be your thumb. Or if you prefer, you can first take your palm, your stop in the name of love palm, point it in the direction of IL, and swing your palm towards B, and then your thumb will be the resultant force. So either one of those two that you want to do, okay? All right, so if you've got some segment of wire, remember that your wire doesn't always have to move in a constant one direction. You can bend wires, you can make them turn around corners, and so on and so forth. And so if you want the total force that a current carrying wire feels in some magnetic field, then you might have to integrate instead over F is equal to I times the integral of I times the integral of ds cross B, where you're integrating over the whole length of the wire. Okay? Now, let's say that we have two wires, and they're parallel to one another, okay? So here we have, in this drawing, wire 1 carrying some current I1, and it's on top, above, slightly above, wire 2 that has some current I2. I1 and I2, we don't know what the magnitudes are, but we do know that they're traveling in the same direction here, all right? Now, what would happen is that wire 2 down here creates a magnetic field. Now, from previous lectures, we know that the magnetic field from long straight wires makes circles around the wire. There's a right-hand rule for this too. So if you take your thumb and you point it in the direction of your current, I2, then your fingers will naturally curve in the circle around the direction that the magnetic field would point. And so you can see here in this image, the green circle represents that natural magnetic field direction. And at wire 1, B2 is kind of pointing out of the screen at us here, okay? So B2 is pointing here. Of course, this is all represented at some angle. So B2 is the green vector there. Okay, now, because there's a magnetic field present caused by wire 2 at wire 1, right? That magnetic field is established by I2, but it exists in the region where I1 is flowing, then there's a force, right, from that magnetic field B2 on I1. That force is governed by the right-hand rule, IL cross B, okay? So if we apply our right-hand rule here, we can see that the force on wire 1 caused by the magnetic field of wire 2 is towards wire 2. So it's an attractive force on wire 1 from the magnetic field created by I2, okay? Now, that magnetic field B2, F1 here, these are all perpendicular. So remember, you've got vector cross products, IL cross B, right? But since everything's perpendicular here, the signs go to 1. Sine of 90 is 1. And so the magnitude of that force F1 would be I1LB2. Okay? I1LB2. Now, we know what the magnetic field from a long straight wire is. So the magnetic field B2 caused by I2 would be mu naught times I2 divided by 2 pi A, where A is the distance in between those two wires. And so we can find what the force is on wire 1 caused by the magnetic field from wire 2. Plugging in there, we've got mu naught times I1 times I2 times L over 2 pi A. Now, this was derived for that very specific case and that very specific geometry, but it is always true that parallel conductors that are carrying currents in the same direction are attracted to each other, whereas parallel currents that are carrying currents in opposite directions repel one another. You can see that if we go back to this other slide here. What we would see is that if I2 were flowing the other way, then B2 would kind of be into the screen. And if B2 were into the screen, applying our right-hand rule, then our force would be repulsive. It would point upward. Okay? So if you have parallel currents, well, they're attracted to one another. Opposing currents, repulsion. You can sometimes express this as a force per unit length on parallel wires. So if you do that, then you just divide out by that L, and you have F over L equals mu naught times I1, I2 over 2 pi A, where A, yet again, is the distance in between those conductors. If you've forgotten, mu naught is the permeability of free space, which is 4 pi times 10 to the minus 7 Teslas meters per amps. So that's just one of those constants of the universe, okay? Now, for a long time, the force between parallel wires was used in SI to define the ampere. And it was defined in this way. When the magnitude of the force per unit length between two long parallel wires that carry identical currents and are separated by 1 meter is 2 times 10 to the minus 7 newtons per meter, then the current in each wire is defined to be 1 amp. Okay? And then the coulomb, the SI unit of charge, was defined in terms of the ampere, right? So if a conductor carries a steady current of 1 amp, then the quantity of charge that flows through that cross-section of that conductor in 1 second is 1 coulomb. Let me do an example problem for you because of course they're worth a million words. The current in the long straight wire is 5 amps, and the wire lies in the plane of a rectangular loop. The rectangular loop carries a current of 10 amps. The dimensions of that rectangular loop are C is equal to 0.1 meters. That's the distance from the long wire to the left-hand side of your loop. And A is 0.15 meters. That's the width of your loop. And L is 0.45 meters. That's the length of the loop. So find the magnitude and direction of the net force exerted on the loop by the magnetic field created by the wire. Okay? Here we go. Now you might be saying to yourself, dirty pool. She talked about parallel current carrying wires, but very clearly here I can see that I've got segments of the loop on the top and the bottom that are also carrying currents that are not parallel. In fact, those two wires right there at the top and the bottom of the loop are perpendicular to I1. So what do I do about that? Huh? Okay, never fear. The force is still IL cross B. And we can figure out what the magnetic field direction is from I1. So the magnetic field is going to be pointing into your screen on the right-hand side of I1. You can see this if you take your thumb and you point it along I1 and you curl your fingers. It's going to point in the direction of the screen on the right-hand side. Okay, so the magnetic field's into the screen. So now let's figure out what's going on the force, what's going on with the direction of the force in each segment of this wire. So here, I2 on the left-hand side of the loop is going upwards. Okay? On the left-hand side, it's going upwards. So if we do I2L cross B, right, then that means that the force on the left-hand side of the loop is to the left towards that other wire. Now that squares with what we said before, so good. Now, on the right-hand segment of the loop, I2, it's flowing clockwise, so it's going to be going down on the right-hand side of the loop. Okay? If you do your IL cross B there, right, then that means that the force on the opposite side is going to be to the right. Now it's further away, okay? It's further away, so it's going to be weaker, but we can figure that out. But we'll draw the arrow right now as a little short arrow pointing to the right. All my force vectors here are in red arrows in case you didn't know. Now let's figure out what's going on with the top and the bottom. Okay, I2, as it comes around the top of the loop, I2 is going to be going to the right. So IL cross B on the top of the loop, the force would be upwards, okay? Now because it's a little further away, the magnetic field's going to be a little bit weaker, so I've drawn my arrow shorter than for the left-hand side, but maybe not as short as it is over here on the right-hand side. I don't know, I'm drawing it there, okay? So the force is up. Now let's talk about what's going on in the bottom. In that case, the force is going to be downwards. IL cross B, boom, down. Okay? Or IL cross B, whichever way you like it better. The force is down. Now, it's opposite to the direction of the top segment. So the top points up, the bottom, the force is down. Now, the top and the bottom are the same distance away from I1, right? So that means that the forces on these segments of the loop are equal and opposite, right? Equal in magnitude and opposite in direction. So the force on the top and the bottom are going to cancel out. Well, you might say, well, the force on the left and the right are in opposite direction. Don't they cancel out? No, no, because they're not the same distance from I1. See, on the left-hand side of the loop, I'm closer to I1 than I am on the right. So even they point in opposite directions, the force on the left-hand side of the loop is stronger. So that means that what's going to happen here is that my loop is going to be net pulled to the left. Okay? That's what's going to happen. The top and the bottom segments cancel out. So now I just need to figure out the magnitude of the force on the left, the magnitude of the force on the right, and subtract them to get the magnitude of the net force on the loop as a whole. Okay? That's my strategy. Let's get to it. The force on the left segment is to the left. I'll call that negative, the negative direction. Okay? So FL here, using my equation, I have mu naught times I1 times I2 times the length L, and then divided by 2 pi times the distance in between I1 and I2, which is C, okay, in this problem. Plugging in numbers for that, I have mu naught, which is 4 pi times 10 to the minus 7, times 5 amps times 10 amps, times 0.45 meters, that's L, and then divided by 2 pi times 0.1 meters, that's C. That gives me negative 45 micronewtons. Remember, the negative sign just means to the left. Now let's find the force on the right-hand side there, the right-hand segment. So that one's going to be to the right, as we've already discussed. I call right my positive direction. So that's mu naught I1 I2 L over 2 pi times the distance in between I1 and I2 on the right-hand segment of the loop. That distance is C plus A. C plus A is 0.25 meters. So when I plug in the 5, the 10, the mu naught, the 0.45, all that stuff, when I plug it into my calculator, I end up with the force on the right-hand segment is plus 18 micronewtons. Now to get the net force in the loop, all I have to do is add those two things together. So we have minus 45 micronewtons plus 18 micronewtons, and that gives me negative 27 micronewtons. Okay? So that's the net force on the loop. Remember, there is a force on the top and the bottom segment, but since it's equal and opposite, it causes no net force in the loop, so I didn't include it here. All right? Okay, I hope that example helped, and I'll see you around. See you in class. As always, let me know if you have any questions. Bye.